This video is kindly sponsored by Tufon. Hey, come here. Did you know there's only 4 types of loads that you need to know as a structural engineer? Do you know what they are? Do you know how they affect your designs? And understanding these 4 principal forces will make any design easier, doesn't matter how simple or how complex. So let's break them down so that you can apply them to your designs. My name's Brendan, your structural engineer. Now let's get into it. So what are the 4 main forces? We've got axial, shear, bending, and torsion. Now it's not quite as simple as that, as they interact with each other. So one can affect the other and change how the behavior occurs. But let's first break down the primary actions and how they can affect your design. Then we'll move into the interactions that they can have on each other. So let's start off with axial. Now, I know what you're thinking. Isn't that the easiest one? Well, kind of yes and kind of no. You see, there's 2 different directions that force can go. You can either go into compression or you can go into tension. Now, how the structure behaves is actually fundamentally different. So we'll break this down into either compression behavior or tension behavior so we can understand it more. Tension, especially if we're dealing with steel structures, is arguably one of the most efficient ways to design things, as steel behaves really well under tension loads. So we're just really stretching it out. It does have different effects about how the elongation goes, because as you stretch it, it will elongate based on PL on EA. So the force times the length divided by area divided by Young's modulus. So when you're looking at continuous structures, not only is it the force that is applied, but how much will it actually sag will determine the tension force in those continuing actions. So if we're looking at a suspension bridge, we can see the nice arch behavior of the structure. It's trying to go into the most simplest form. The tighter it goes, the more force it needs to have to resist the same load. So that parabolic arch is actually helping us reduce the stresses and making our building more efficient. So the tension forces is arguably the easiest one to understand. You just really stretch it and it stretches until it breaks. At which point it's over, right? You just stretch it and it's gone. Compression, on the other hand, gets slightly more complex. So compression, when you're going down the basic principles of it, it's a little bit easier. You're just compressing that force. So when you got a shorter section, it just holds until it either crushes or buckles. Now this is where buckling becomes a problem, because potentially the length of it and the slenderness of it will affect the behavior. So a more slender structure can take a lot less load. And we can see this when we apply stress to a ruler. You can see it bending down as the force is applied. Where if we go to a more rigid structure or a shorter structure and we apply that same compression force, it holds it a lot better. So when you're looking at a compression load, you need to fundamentally look at how long is my structure? Has it become slender? And now do I have a critical buckling bending failure? Because if you have a critical buckling bending failure, that is going to be the failure load, not actually the section member. So you see, compression, despite thinking it's a lot easier, it's actually a little bit more complex than your tension actions. Now we'll break down something that's even a little bit more simpler, and this is bending forces. So what are bending forces? Well, when you apply a load on a beam, it will bend down. You can see that the top is getting shorter and the bottom is getting longer. So this is causing a differential between the top and the bottom. So when you're looking at the stress diagram, at the top it's in compression, at the bottom it's in tension. So it's the difference between the top and the bottom. So this is what you can see when structures deflect. They must have seen some sort of bending forces applied to them. Now, bending actions are quite simple. Potentially you only need tension on one face and compression on the other. So if you're always going to have a bending action, potentially you only need to apply the tension loads on one side of the structure and put tension strengthening on that. Now, if you're talking about something like a steel structure, it's not as complex, as you potentially don't need to change how it behaves. But something like a concrete structure, this is really fundamentally important to know which side is in compression and which side is in tension, as you need to reinforce the tension face to stop the concrete from cracking, which is no good in that tension actions. But where on the compression face, you can potentially reduce it if it's always in compression, as it will not crack, it's holding it together. Bending actions is also really good when you're looking at to PT action. If you understand where the bending force is, where the tension face is, and where the compression face is, you know where you need to drape your tendon, as you want the tendon closest to the tension face as much as possible, because it compresses that face, stopping those tension actions from inducing either cracking or fundamentally critical forces. So if you know which way the bending moment diagram is going, making sure that you're putting your PT tendons on that face is something that's really important to how you're designing the structure. This video is kindly sponsored by Tufon, who's kindly supplied me this 3-in-1 charger that allows you to charge your iPhone, Apple Watch, and AirPods all in one easy dock. It has multiple safety protections for overcurrent protection, temperature control, radiation shielding, and foreign object detection. As it uses both magnets and wireless charging, you can charge both in a portrait view and a landscape view without any effort. And you're able to change the angle from 35 degrees to vertical to get the perfect viewing angle wherever you need it. Another great thing is the single point of charge, and allows you to charge 3 devices at once, so it cleans up that messy desk, and because it supplies a 20-watt charge, you can fast charge any devices that you have on there. It's all FCC compliant, and you don't need to worry, has all the highest safety standards that you need. If you're interested in this product, I've links in the below description that you can click on to pick up this product today. Now let's get back to the content. But when we're talking about bending forces, we must move into shear because they do interact. And we'll start off with transverse shear to start off with, as we're just talking about bending actions. As we saw, the structure was on an angle, so the top was in compression and the bottom was in tension. But you can see there's a stress gradient through that. It means that each plane must slide on top of each other. It's like a book. When you bend the book down, you can see the pages sliding on each other. So there's this stress between each of the planes to apply that bending action. So if you have a weaker plane, potentially you need to reinforce through those joints to stop those transverse shear actions from occurring. So there's an interaction here to allow you to have those bending actions and have as stiff a structure as possible. You need to make sure those plates sliding on top of each other have enough strength or reinforcement through them. Most of the time this is not so critical, as things like concrete or structures that are solidly built together, you don't need to worry so much. This is unless of course the shape changes through the height of the structure. Now, the one place that transverse shear is super critical is when the section changes based on its height. So if you've got a T section of a beam, you have to watch out about the plane just before the T sections occurs, as the top section will be in more compression. So there's more stresses that need to apply through that interface. So you need to check whether you have enough reinforcement through that joint to allow those transverse shear forces to occur. Now that's just the transverse shear. The primary action of shear is not really transverse shear, that's more a secondary action, but it's real shear behavior. You've got those axial forces, you've got the bending actions, but you also got the shear behavior. So if we've got a beam spanning from left to right, that vertical force needs to go somewhere to go to the supports, as you need to have the bending action to stop the structure from bending down and changing. And likewise, you need to change that shear force to make sure that shear force is transferring from that point to the points of support. So it becomes into a strut and tie action where the force goes down, causing the bottom action to be in tension, the top action to be in compression, but then you also have these diagonal forces to finish off that strut and tie action to transfer those vertical forces through. So that means there's a corresponding diagonal struts going backwards and forwards to the supports to change that action. So it's the structure trying to pull apart. Now, typically where this is most critical is at the supports, where you see the highest concentration of loads. And when you know you have a shear action, you've got to watch out for those diagonal cracks. Because of the way the behavior works, it's causing a diagonal cracking along the strut as the force is trying to rip the section apart. So the way you deal with this is typically in reinforced structures is to have vertical lines of support through there. Now it's not as efficient as if you went on an angle because you can see the direction of the crack, but it's a lot harder to reinforce as you don't fundamentally know necessarily which direction the crack's going to go, but it's just about stopping that plane from occurring. Now shear is fundamentally the worst type of failure you could have, other than potentially a compression failure, but it's brittle. It means that a lot of times you don't get any warning as opposed to a bending force. So bending force is in tension, you can allow the structure to yield and you can see the behavior occurring before it's too late. Where shear will typically hold on, and then it's gone. So this is why we have more factors of safety on a shear force than we do on bending actions. So what's the last type of force? Well, this is torsion. Now torsion is causing a twist on your structure. If you've got an offset load, the structure needs to pull it back to stabilize the building. And there's two different types of torsion that you can have. You can either have compatibility torsion or principal torsion. So compatibility torsion is something that occurs in typically a flat plate slab. You've got this big building, and because of the twisting behavior and the 2A actions, you're getting a torsion force. But you can release that torsion force and still have the structure stable. It means that the structure does not require those torsion actions to be stable, as there is another load path there based back in the bending forces, shear forces, or axial forces. So we're able to resist it in another way. This is typically preferred. You want to typically try and avoid torsion, as a little bit of twist can have a big effect on your structure, but it's not something that you want to ignore. The other one is the principal torsion, which is needed for structural stability. You'll see this potentially if you've got a beam with a cantilever coming off it. There's no other way than to resist those forces from the torsion action, that you need to reinforce for them to make sure the loads can be transferred back to the columns. So when you've got the torsion action, not only do you have to worry about the beam and reinforcing for it, but you also need to make sure that at the supports there's a fixed connection to stop that torsion actions to occur in some way, as you need to fundamentally stop the load path and have the loads go back to those principal forces that we talked about earlier. Torsion is one of those things that every engineer hates. As the reinforcement is high, the behavior is super critical as it affects your bending so much. So it's something that us as structural engineers try and avoid through good detailing. So it shouldn't be your first point of call, it should be your last point to try and achieve the architectural freedom. There's a simple rule to structural engineering that you probably didn't know about that will make your designs better, simpler, easier, and more efficient. And I'll link that video here, and something that every engineer should know. And if you want to support this channel, there is 2 ways that you can do this. You can either become a YouTube or Patreon members. Without the support of my YouTube and Patreon members, this type of content would not be possible. As always, keep learning, and I'll see you next week. Bye.